Okay, so before we start with writing some actual CUDA kernels, we need to understand how memory works on the GPU. So this has gotten a lot easier to get started with programming on GPUs with CUDA 8 in particular, and the use of what we call a unified memory. But if we look at a node on Piz Daint, this is the same picture we had before. You can see we had our what we call our host CPU processor, and it has its memory. In the case of Piz Daint, it's got 64 gigabytes of memory. And then we have our GPU over here, and this connection, I should have labeled it, this is over the PCI bus. So it's connected over the PCI bus, and the GPU has its own 16 gigabytes of memory. So it's always been true that the GPU typically has much less memory than the host CPU. And we need to be aware that these different memory spaces exist and be able to move information between the memory spaces or understand where information is if we're going to be able to program these nodes effectively. So, as I said, the GPU and the CPU have separate memory. And kernels that are running on the GPU can only access memory that is in the GPU memory space. It's technically, as we're going to say with universal memory, we might actually, unified memory, we might have some memory that's on the host in the 64 gigabyte partition, and some code running on the GPU might try to access it, and that's okay. It's going to copy, that information will get copied over from the host memory to the GPU memory. However, that information has to be copied over the PCI bus onto the GPU memory before the GPU can access that information. So even though unified memory makes it look like, and we're going to see more about this later on, even though sometimes when we're programming for the GPU it might look like it doesn't matter where memory is for it to get accessed, at the end of the day, if the GPU wants to use some information, or if the host CPU wants to use some information, that information has got to get copied into that memory space. And when we want to copy information from one memory space to another, we have to do it over a very slow PCIe connection. So this is the bandwidth. So memory bandwidth is the amount of information, is how quickly you can copy information from one inside that memory space. So typically it's the host memory, so I actually sat down and wrote a little benchmarks to measure these. So these are the actual speeds that you would expect to get. For the host memory, our 64 gigabytes of DDR4, you can copy information around at a speed of about 45 gigabytes a second. The GPU memory is 558 gigabytes a second, which is enormous. This is one of the biggest upgrades, one of the big upgrades over the previous GPU, because the K20 GPUs, when you actually measured the performance, you got about 185 gigabytes a second. That's been pushed up to 558 gigabytes a second, so very fast. The problem is, if we're copying between host and device on the PCI Generation 3, we get about 11 gigabytes per second copying from host to device or from device to host. This times 2 means we can actually be copying from the host to the device memory at the same time as we're copying from device back to host. So we can actually be having one copy going in each direction, and each direction has a full 11 gigabytes available to it. But if you're only copying, if you're only copying in one direction, you still only get that 11 gigabytes a second. So this is a key optimization tip, is that you've got this massive bandwidth on the P100 GPU, and for a lot of algorithms and codes, that's really useful. But this is only going to work for you. You're only going to be able to use that bandwidth if the information is already on the GPU in the right memory space before you start executing. Because if you have to copy it over this skinny little pipe here, you're going to lose all performance benefits. So unified memory is a programming model, an API, which presents the memory as being both the host and device memory as being one single unified memory space. And this makes it, this is a big improvement makes it much easier to program. So now if we use unified memory in CUDA, we basically allocate some memory and then we can use it for GPU code, for CPU code, and the CUDA runtime looks after making sure that memory gets copied around to where it's needed when we need it. And so it presents a single memory space, and the CPU and the GPU both have access to this memory. It was first introduced with CUDA 6 on the Kepler architecture. But with CUDA 8 and Pascal, it has been, let's say, it's been improved a lot and it's been made feature complete to the point where it's actually, I think, really quite useful now. In that all memory on the host and the device can now be addressed by both host and device. And there's a page migration engine, which I don't know if Peter's going to go into low-level details about it. I'm not going to go into low-level details about it here. But there's an engine underneath that automatically handles the transfer of information between GPU and the CPU. So, for example, if you've got some memory that you've allocated into this unified memory space and it's been put in the host memory, the CPU memory, and then the GPU requests, says, I would like to read a value from that memory, what this page migration engine will do, there will be a page fault where the page of memory that information lies in, a page fault will be triggered saying, this memory I wasn't able to access it, and the page migration engine will actually say, well, I'll take that page of information, which is a 4 kilobyte chunk, and I'll copy it over the PCI bus onto the GPU, into the GPU memory, and then the GPU will be able to use that information. And it's the same going the other way. If the CPU tries to access something that's a page of memory that's stored in the GPU memory space, it will automatically get copied over for you. The problem is that this has got a massive latency on it, so we want to avoid this happening, but it's still a very nice, it's a very good way to start developing your application, because one of the most annoying and tricky things about really writing CUDA applications and doing porting, taking an existing application and adding CUDA features to it in the past was dealing with the two separate memory spaces and having to manually copy information around. With managed memory, it's much easier to start porting code and start getting things to work. And then, and we're going to see this, you can use the profiling tools to see where you're having problems with, say, this page faulting and optimize. It also provides an API for fine-grained control of page migration. So we're not going to go into this here, but there are lots of advanced low-level features where you can say, I'm using this memory on the GPU, on the CPU now, but I know that the next time it's going to be used on the GPU, so you can start copying it over to the GPU now, so that it's hopefully going to have arrived on the GPU before it's needed. So when we're using CUDA to access memory, or when we're talking about accessing memory in CUDA, we use pointers. We use C pointers. There's no magical types or anything under the hood here. It's a 64-bit memory address. So, for example, this is how we declare a pointer in C. Its name is data, and it's a pointer to some doubles. And over here, this is going to be a 64-bit address. And that address will be either in the host device or managed memory, and the CUDA, and this is automatically handled for you. So, as I said, a pointer can hold an address. If you allocate memory that's explicitly in the host, then that pointer will be pointing to an address that's in host memory. If you allocate a pointer saying this is explicitly memory that's on the GPU, on the device, then you'll have a pointer to device memory. Or you can allocate a pointer to managed memory, and then you can let the page migration look after moving information around. And the CUDA runtime library provides some functions that we can use to allocate memory and free memory and so on. So just like when we're programming in normal C, if we want to allocate memory, we would use malloc or new, and if we wanted to free the memory, we would use free or delete. Well, if we want to, managing managed memory, that's not such a good title. If we wanted to work with working with managed memory, the first thing we want to do is allocate the memory. And there's a function called CUDA malloc managed that you can use to allocate the memory. So it takes 3 arguments. The first argument we'll look at is size, which is the size, the number of bytes that we want to allocate. And yeah, I always emphasize this, it's the number of bytes you want, not the number of doubles you want or number of floats you want. Pointer, which will be a pointer to the memory. So when we finish, when CUDA malloc managed returns, pointer will be pointing to a location, the memory that was allocated. And then flags, we can pass additional flags. We're not going to go into these in detail here. Maybe on the last day I might present some slides about them if people are interested. But these flags are for use when you want to start doing more advanced things with, say, prefetching information, like I mentioned before, where you would say, I know that I'm going to want this information that's currently on the host to move to the GPU for the next time it's accessed. So I need to, I want to start initiating that copy. You have to start using things like these flags when you want to allocate memory with that property. But this has got a default value, so normally we can just use these 2 arguments. Now it differs, it's a little bit different from using malloc, the normal malloc, because normal malloc we say, you know, pointer equals malloc and then the size, and that's all. This takes 2 arguments here, a pointer to a pointer and the size, and that's because all of these functions, they return an error code. So you can check when you can look at this error code to check whether the memory allocation was successful or whether there was an error. And then freeing the managed memory is a call to CUDA free. So these are the 2 functions, and you can think of them as being equivalent to malloc and free. So here's an example of allocating memory for 100 doubles in managed memory. So we declare our pointer, which we're just going to call v. We calculate how many bytes we're going to need to allocate. Because if we're storing 100 doubles, we need 100 times however many bytes are in a double. So that's 8 bytes. So this is going to be 800. And then we call CUDA malloc managed. We take the address of the pointer because we need a pointer to a pointer, because it basically has to put the pointer inside the pointer. It has to put the correct address inside the pointer. It's one of those annoying things about C++ or C, having to work with these pointers to pointers. And then the size of the memory we want to allocate, and then in between here we would do something with that memory, run some GPU code, and then when we're finished with it, we call CUDA free. So that's pretty simple. Has anyone got any questions? Okay, no questions? So I'm just going to check what time it is. Okay, we've got some time to start working on the first little exercise. So this exercise does not involve any programming yet, but it does involve looking at the source code and trying to figure out what it does. And you can feel free to ask Google. So I'm just going to actually log on and do the first steps again. Okay, so here I am inside the path where we set stuff up before, and I'm going to move to the API directory. Now, is everybody comfortable using Vi or Emacs? Do we have any people who need help? Sorry, I just assume that everybody can do that, but that's not necessarily true. So, yeah, the util.hpp file has got a set of little utility wrapper functions that we use throughout these exercises to make our life easier. And I think this part here, we're just reading some command line arguments. So the user passes in an argument, and then we calculate this size Tn, which is equal to 1 shifted to the left pow, which basically means 2 to the power of whatever. So the user passes in an argument, and this is a common pattern we're going to see in many of the examples. They might pass in an argument like 10, and then the size of the problem we're going to solve is 2 to the power of 10. And this is very nice for later on when we want to test how fast things are, because we can just go 10, 11, 12, 13, and we're just making the problem twice as big each time. So this is just setting up the code. I wouldn't worry about this bit. We call this malloc managed, and then we call this function here with that memory. Okay, so the lunch has arrived. So if you're close to figuring out what it does and you want to keep working on it, keep working on it. We're going to, and then after we come back, I'm going to walk through the example, and then we're going to run the CUDA profiler on the code and have a look at what's happening.